Hello, welcome back. This is Jonathan Gardner covering section 2.4 of Schroeder's An Introduction to Thermal Physics. And this section is quite long. So in the last section, in previous sections, we looked at how the number of ways that you can arrange the energy units is related to, well, how the energy actually distributes in a system, because we assumed that the energy will randomly distribute itself. And so we looked at the cases where there was a few atoms within the system, and we saw that there was some energy orientations or allocations that were much more probable than others. And as we increased the number of atoms, or the number of degrees of freedom, we saw that the likelihood of that most probable situation became much more likely, while the sharpness of the distribution increased. So for instance, we would see something like this. We would see like a curve like that when we had a few hundred degrees of freedom. But when we go to a few thousand, we're going to see that it gets much sharper, right? And then we want to know what happens when we get to like Avogadro's number. Like if we have that many degrees of freedom, how sharp does it get? What is the likelihood of seeing the energy allocate itself in a way that's much different than the most common way? So in order to do that, we need a new kind of math. We need a math that allows us to calculate basically n factorial, where n is a very large number. And that's not an easy thing to do. So to begin with, we're going to talk about very large numbers. So there's three kinds of numbers we're going to use in this section. The first is small numbers. These are numbers that you are familiar with. And then we have large numbers. These are numbers that are so big that when you add a small number to them, they're basically equal to that large number, okay? So adding a small number to a large number has no effect, okay? And then you have very large numbers, where if you multiply a very large number by a large number or a small number, that's the same as doing nothing at all. So this should be strange behavior to you. It should make a little sense, though. An example of a large number he has is 10 to the 23rd, which is on the order of Avogadro's number. And if we just add 23 to that, that's the same as 10 to the 23rd, right? That 23 really makes no difference. And for a very large number, he gives an example of 10 to the 10 to the 23rd. And if we multiplied that by, let's say, 10 to the 23rd, by the way, this is 10 to the 10 to the 23rd. It's not 10 to the 10 to the 23rd. Then that is going to give you basically 10 to the 10 to the 23rd plus 23, which is just the same as 10 to the 23rd, which is like not multiplying by nothing at all. So these are numbers that are extremely large. And hopefully, like even this number here, this number is beyond astronomical, right? So we're talking like we're way beyond the number of stars in the galaxy. So these numbers are huge. These numbers are absolutely fantastically huge, okay? Now, one of the tricks that he says is instead of dealing directly with the large numbers, we often deal with the log of these large numbers. So 10 to the 10 to the 23rd, that's going to give you 10 to the 23rd times a log of 10, right? And multiplying 10 to the 23rd by a log of 10, you might get 10 to the 24th or something like that. So you might have some significant effect upon that number because it's not a very large number. So we like to take the very large numbers and reduce them down to large numbers using logarithm. Problem 212 is a little bit of homework to remind yourself about how logarithms actually work. If you can't easily answer these, then you need to restudy logarithms. There's a section in basic mathematics where I cover that. Problem C is about the derivative of a logarithm. This is one of those basic derivatives you learn in calculus early on. And D is derive the useful approximation that log of 1 plus x is about equal to x. I'll just put equals to x, okay? This is an interesting thing to know. You can use a calculator to verify for that. Problem 213 is doing some fun with logarithms. So this one will show up as in this lecture, e to the a log b, okay? I want you to spend some time doing that. It would be fun to do. I did it myself. I wrote it in the margins actually on page 64 because it was confusing me. And then the other one that they want you to look at in problem 213 section B is if b is a small number compared to a, or if a is a large number compared to b, then the log of a plus b will give you something close to the log of a plus b over a. And you can prove this rather easily using this identity up here. Oh, I'm sorry, this only works when x is much smaller than 1. So when x is a small number, or when 1 looks like a large number compared to x. The next thing we're going to cover is something called Stirling's approximation. And what Stirling's approximation allows us to do is take the factorial of a very large number, and that'll give us a number that's somewhere in the neighborhood of n to the n times e to the minus n square root of 2 pi n. Another way to look at this is it's n over e to the n times the square root of 2 pi n. Okay. Now, for very large numbers, sometimes we drop this factor, right? Because this is only a large number. While this, if you're taking a large number, a number raised to a large number is a very large number, and so we can drop that. So we can often substitute that with n over e to the n and get the same answer. You know, it's not going to really change very much, okay? Remember that we're often interested only in the logarithm of these large numbers. So if we take the log of n factorial, that's going to give us something close to n log n minus n, okay? So that's another way to write out this n factorial when you're taking the log of it. The fun thing about the Stirling approximation is he has a little table here where he plugs in some numbers, and he says it's pretty accurate. You don't have to get n very large to see how accurate this thing is, right? For instance, when n is 100, n factorial is something like 9 times 10 to the 157th power. And the approximation with the factor of 2 pi n, the square root of 2 pi n, gives you same thing, n times 10 to the 157. And the error is only, you know, less than 0.1%. So it's pretty small. Logarithm as well, when you take the logarithm of 100 to the factorial, you get 364. And n log n minus n is 360, and so that's only an error of 0.89%. So this is very accurate. So problem 215 is to check it out for n equals 50, and problem 216 is to flip 1,000 coins, see what happens, how likely it is to get 500 heads and 500 tails. And if your calculator, your computer is strong enough, you can probably just calculate this directly using the 500 factorial or whatever. However, he encourages you to, if your computer can calculate it, then bump it up from 500 to 5,000 coins or 5 million coins, some large number that will cause your computer not be able to calculate it. And problem B of problem 216 is to see what happens when you have 600 heads and 400 tails. At this point, we have the tools we need to analyze an Einsteinian solid and see what happens when the number of particles and the number of available energy, the amount of total energy increases. So the multiplicity we've calculated before, omega of n degrees of freedom and q energy, that's just equal to q plus n minus 1 all over q, which is exactly equal to q plus n minus 1 factorial all over q factorial times n minus 1 factorial, okay? And we can approximate this by removing that nasty 1 there. So we get q plus n factorial all over q factorial n factorial. So we're just removing one of these terms, right? Let's take the log of omega, which is the log of q plus n factorial over q factorial n factorial using the approximation here. Then we would see that that is equal to the log of q plus n factorial minus the log of q factorial and minus the log of n factorial, okay? And this is just basically because we know that log of a b is equal to log of a plus log of b, and log of a over b is equal to log of a minus log of b, okay? So we're subtracting the two factors in the denominator there. We're going to use the approximation for very large numbers, the approximation being that log of n factorial is equal to n log of n minus n. And so this is going to reduce down to, well, we take this one, so we get q plus n times log of q plus n. minus q plus n. All right, then we have the log of q factorial. So that's going to be q times log of q. This is all minus, by the way, minus that. So q log q minus n log n minus n. Okay, so you can see that this is a minus q, this is minus a minus q, so these two terms are going to cancel. A minus n here and a minus minus n, so that's going to cancel. So we get q plus n of log of q plus n minus q log q minus n log of n. At this point, we can go back to what we did in problem 213, part B, and we can replace the log of q plus n with the log of q times 1 plus n over q, which is going to be about equal to the log of q plus n over q. That's using the approximation. And this only works because the ratio of n over q is much smaller than 1, right? We're assuming that n is much larger than q. Well, it doesn't have to be much larger, but it's large compared to. So we get this is equal to q plus n times this, log of q plus n over q, minus q log q, minus n log of n. And so we can distribute some things out. So we're going to get a q log of q term. We're going to get an n log of q term. We're going to get q times n over q, so we get an n, and we get an n squared over q. We have a q log q here. We have an n log of n here. So this term and this term cancel. Continuing on, I'm going to scroll this up and add another piece of paper at the bottom here. So we get n log of q minus n log of n. Then we have an n term, and we have an n squared over q. So this is n times log of q minus log of n, which is n times log of q, if I can write a q, over n. And then we can't forget that we have this n and n squared term over q. Sorry about my handwriting. So this is equation 220 in the book. Okay. The next step is we say that as q is much greater than n, and we call this the high temperature limit. And by high temperature, we don't mean like molten lava temperatures. We mean like not cryogenic temperatures. So temperatures that are normal, right? So when Q is much greater than N, so there's much more energy than there is the number of ways, there is the degrees of freedom that you can allocate that energy in. Then we can eliminate this last term. So N squared divided by Q, we can eliminate that term because it is negligible. Then we get, this is N log of Q over N plus N. And remember that this is the log of omega, right? So omega itself is equal to e to the n log of Q over N plus N, which we can just write that as e to the n log of Q over N times e to the n. Okay. Now for this term here, we're going to remind ourselves that e to the a log b is the same as b to the a. If you want to prove this for yourself, what I did is I took the log of both sides, basically. It's pretty straightforward. So we get this is equal to e to the a log b is b to the a. So Q over N to the n times e to the n. And we can bring that e to the n side, so we get e Q over N to the n. And that's how you derive formula 221. Now, let's look at this really quickly and see what happens as we change the numbers. So what happens to omega as Q increases? So as you increase Q, omega is going to go up by Q to the n. Okay? what if we increase the number of degrees of freedom? So as the number of degrees of freedom goes up, then we're going to see that this goes up by q over n, well, eq to the n, the exponent of n. So this is like increasing the degrees of freedom has a huge effect on the number of states that contain that, right? But increasing q doesn't have as large an effect. You'd think that adding energy to a system would cause the number of ways to allocate that energy would go up, but no, it's actually increasing the number of degrees of freedom has the hugest effect. Let me put that in a different way here. So increasing the energy in a system, the total energy, doesn't increase the multiplicity by as much as increasing the degrees of freedom. Okay, we have problem 217 now, where you can try to do the same thing, but this time assume that Q is much less than N. This is what we call low temperature. Okay, and this is like the cryogenic limits. We're talking about energy that's near like zero, like absolute zero. Okay, 218 says use Stirling's approximation showing Einstein's solid for any large values of n and q is approximately equal to this complicated function, right? So in problem 218, we're using Stirling's approximation to do some complicated math. It's mostly just algebra, pretty straightforward. In 219, using Stirling's approximation to find an approximate formula for the multiplicity of a two-state paramagnet. Okay, so this isn't that hard. This is fairly straightforward, using the same formula that we've used before and same kind of math we've done. Let's talk about what happens when we do the multiplicity function. And we want to see like how likely it is that if we have two systems with the same number of degrees of freedom, how likely it is that the energy is actually allocated 50-50, right? In other words, we're going to calculate what the maximum multiplicity is, and we're going to calculate how far we can move away from that before seeing a significant decrease in the multiplicity. So as you recall, the multiplicity total is a multiplicity of A times the multiplicity of B, and we're using an Einsteinian solid. So we've calculated the multiplicity is going to be E times Q over N to the N, right? And so Q is the amount of energy that we have, N is the number of degrees of freedom. So the total of two Einsteinian solids put together, we're going to have EQA over N to the N times E times QB over N to the N. And if we have Q, we have the situation where NA, this is the situation where NA equals NB, so we're just going to call that N. Okay, so they have the same degrees of freedom. Okay, and if we calculate this out really quick, we get the pleasant result that we have this E over N term raised to the 2N. This doesn't change, but we also have this QA times QB to the N. Okay, now obviously we're going to guess that when QA is equal to QB is equal to total energy over 2, that's the most likely situation. So the maximum multiplicity is going to be E over N to the 2N, and then we're going to have Q over 2 squared, basically. Okay, so this is the maximum multiplicity. That's the peak, right? Okay, so we have the max, the peak is going to occur with a multiplicity of Q over 2 to the 2N, right? Now what I want to calculate is if we take QA is equal to that half energy plus X and QB is equal to that half energy minus X, what happens? So we get omega total is going to be E over N to the 2N times QA, which is Q over 2 plus X, QB, which is Q over 2 minus X, and all of that is raised to the nth power. Okay, then using simple algebra, this becomes Q over 2 squared minus X squared to the nth power. Okay, so at this point, what I'm going to do is I'm going to take the log of both sides, and we're going to have the log of E over N to the 2N plus the log of this mess, Q over 2 squared minus X squared to the nth power. And the reason why is I want to see basically I want to rewrite this in a different way. Okay, so we take the factor of q over 2 squared out, so we get q over 2 squared 1 minus 2x over q squared. Okay, that's raised to the nth power. Okay, we can actually, let's move this in out front. Okay, we could do that. Okay, and so this is going to be equal to plus n log of this one, so log of q over 2 squared plus n times the log of 1 minus 2x over q squared. Okay, this one here, we're going to use the approximation that log of 1 minus x, log of 1 plus x is about equal to x when x is much less than 1. Okay, in this case, we have a very small change compared to the total energy. So this is going to be n times minus n times 2x over q squared. Okay, and all of this stays the same. Okay, now we're going to take e to the both sides, so we get omega is equal to e over n to the 2n times e to the n log of q over 2 squared times e to the minus n of the 2x over q squared. Okay, now we had omega max up here. We can rewrite omega max in this way. We're going to change this to e to the n, e to the 2n log of q over 2. Okay, and then we can take that 2 and bring it on the inside. E to the n log of q over 2 squared. And so this part and this part look the same. Okay, so we'll just write this out as omega max times e to the minus, and I'm going to write it out this way. So n times 2 over q squared times x squared. Okay, and this function here, this is a Gaussian. I'm sorry, not a q. Okay, Gaussians take the shape of f of x is equal to some constant times e times some constant minus b to the x squared. Okay? Now when we analyze the Gaussian, we're going to be interested in how wide that peak is. So we know that all Gaussians look the same, right? They all go up and they come back down like this. And there's the average, and then we're going to have some kind of width here, right? And so the question is, what is the width of this peak? So let's take this n 2 over q squared, x squared. Let's take that equal to 1. Okay. Then we get x squared is equal to 1 over n q over 2 squared, I believe. Yes. And we take the square root of both sides. We get x is equal to q over 2 times the square root of n. Okay. Now, when x squared, when this is equal to 1, then we have dropped down by 1 over e. So f of this value, let's call this a. Mu plus a is equal to 1 over e times f of mu. So it's just by deviating by this much, you're going to drop by 1 over e. So this factor of 1 over e. Okay. Now, when we're considering the fact that n is on the order of 10 to the 20th, okay, that means the width of this curve is so tiny, right? If we were to draw the graph out, so we're like 10 to the 5 kilometers is the size of the graph. And then we were to find there in the middle, how wide would that be? The width would be about 1 centimeter. Okay, that's how tight this is when you get these numbers that big. Let me scroll that up so you can see that. This is the conclusion. This is the reason why when we talk about the second law of thermodynamics, when we say that it's most likely that the energy is going to organize itself a particular way, such that it's equally allocated if they have the same number of degrees of freedom, such and such. We're not talking about it's very unlikely you're going to see something else. We're talking about it's impossible. It's never going to happen. Okay? When the graph is this tight, it is a very, very safe assumption, right? Assuming that QA is equal to QB in this case is equal to the total energy over 2. This is basically true, right? Because you're never going to see another allocation. It's never going to happen any other way, okay? So this is what we mean. You might hear somebody say the thermodynamic limit. And what the thermodynamic limit is that's a fancy way of saying that we're dealing with numbers so huge that the probabilities, even though they exist, are so small that they're meaningless. We don't even think about them, okay? So problem 220 is if you were to take this 10 to the 5 kilometer graph and shrink it down to the size of a page, how wide would that be? And that's just a simple multiplication problem. Problem 221. You can actually graph this out using a computer. And he wants you to do that. He tells you how to do it. And that problem 220 is pretty good if you really want to get a feel for how tight this graph is. 222. Here is an alternative way to estimating the width of the peak of the multiplicity function for a system of 2 large Einsteinian solids. And he walks you through a whole process. Here, I won't cover it. It's very interesting. And 223, paramagnets, you can do that. 224, again, more to do with paramagnets. Multiplicity very sharply peaked. Yeah. And then because paramagnets are related to coin flipping, because it either is up or down, you can use the same logic to figure out how likely it is if you flip 1,000,000 coins to have, like let's say 501,000 heads and 499,000 tails, right? And 225 talks about random walk, which is a good thing to do and figure out. These are problems that, I don't know if your professor is assigning them to you to torture you, probably not, but he's probably assigning them to you so that you can expand your mind, so that you can try this mathematics out, so you really understand the kind of reasoning that we're using for this kind of logic. Anyway, that's section 2.4. It is kind of long. There's a nice little quote here at the end by Ralph Behrlein. He says, it all works because Avogadro's number is closer to infinity than to 10. And if you don't understand why that's an absurd statement, infinity is much larger than Avogadro's number. In fact, Avogadro's number is no closer to infinity than 1 is, and 10. But, it is a huge number. So we get to do that. We get to do something there. Anyway, next section, we're going to do the ideal gas. And we're going to see how we can use the things that we've been talking about here to analyze an ideal gas. It's going to get fairly strange. We're going to start diving into quantum mechanics. We need to rely on quantum mechanics because we have to count things. But it should be very fun. And then after that, we can actually talk about what entropy actually is. So guys, have a great day. Take care, and bye-bye.